The history of theoretical physics in the 20th century is often told as a series of abstract revolutions: relativity, quantum mechanics, and the quest for a unified field theory. Yet standing apart from the great theorists was a man who viewed the cosmos through the lens of a mathematician and the pragmatism of an engineer. Freeman Dyson, a figure who spent over 60 years at the Institute for Advanced Study in Princeton, redefined the boundaries of what is scientifically fit for study. He did not merely seek the fundamental building blocks of matter. He sought to understand the operational limits of reality itself. Whether analyzing the survival rates of bombers in the night skies over Germany or the survival of intelligence in the heat death of the universe, Dyson's work was anchored in two specific angles: the hard limits of engine efficiency and the operational application of thermodynamics. To understand Freeman Dyson's professional obsession with limits, one must return to the year 1943. At the age of 19, Dyson was a mathematician at Cambridge, but the war effort diverted his talents to the Royal Air Force Bomber Command. He joined the Operational Research Section, ORS, a group of approximately 50 scientists whose mandate was to bring the rigor of the scientific method to the chaos of aerial warfare. This was Dyson's first encounter with operational thermodynamics, the study of how complex systems perform, fail, and dissipate energy under extreme conditions. Working under Reuben Smead, a meticulous statistical analyst, Dyson was tasked with understanding why so many British bombers were failing to return from raids over Germany. The data was grim. The RAF's primary heavy bomber, the Lancaster, was a marvel of aeronautical engineering, but it possessed a statistical flaw that Dyson found unacceptable. While American B-17 crews had a 50% chance of bailing out successfully if their aircraft was hit, the escape rate for Lancaster crews was a meager 21.3%. Dyson's investigation did not focus on the physics of the flak or the trajectory of night fighters. Instead, he looked at the engine of survival, the escape hatch. He discovered that the Lancaster's hatch was too narrow for a pilot wearing a bulky parachute to exit quickly under the G-forces of a spiraling aircraft. This was a classic efficiency limit. The system of the bomber was efficient at carrying payloads, but catastrophically inefficient at preserving its most vital components, the human operators. Despite producing an extensive manuscript titled Operational Research in Bomber Command that detailed these shortcomings, Dyson watched as the bureaucracy of the Air Ministry prioritized production over modification. The war ended before a single hatch could be resized, leaving Dyson with a lifelong skepticism toward large-scale bureaucratic science and a deep respect for the unforgiving nature of physical constraints. The development of the bomber stream was perhaps the most elegant example of Dyson's operational thinking. The German defensive system, the Kammhuber line, relied on individual cells where a single ground controller would guide one night fighter to a single target. By concentrating hundreds of bombers into a narrow corridor, a stream, the RAF effectively saturated the processing capacity of the German defense. This was a transition from individual events to a statistical flow, a concept that would later underpin Dyson's work in statistical mechanics and the energy utilization of advanced civilizations. After the war, Dyson transitioned to the theoretical heights of Cornell University and the Institute for Advanced Study, where he worked alongside Hans Bethe, Richard Feynman, and J. Robert Oppenheimer. His most famous contribution to pure physics was the unification of the three versions of quantum electrodynamics, QED, proposed by Feynman, Julian Schwinger, and Sein Itiro Tomonaga. Dyson proved that Feynman's intuitive path integrals and diagrams were mathematically equivalent to the more traditional operator formalisms of Schwinger and Tomonaga. This unification was more than just a mathematical exercise. It was an attempt to find the elegant mathematics that governed the interaction of light and matter. For Dyson, QED represents the ultimate efficiency limit of the electromagnetic field. He was particularly impressed by the work of Bethe and Heitler on Bremsstrahlung, braking radiation, which he regarded as the most important achievement of 1930s QED, because it described how particles lose energy when they are accelerated or decelerated, the fundamental friction of the subatomic world. However, Dyson's heart remained in the operational. In the mid-1950s, he joined Friedrich de Hoffmann and Edward Teller at General Atomics to design nuclear reactors that were intrinsically safe. The result was the TRIGA reactor, training. Research, isotopes, General Atomics. The thermodynamics of the TRIGA were unique. It used a uranium-zirconium hydride fuel that possessed a large, prompt, negative temperature coefficient. As the fuel heated up, the zirconium hydride would moderate neutrons less effectively, automatically slowing the reaction without the need for mechanical control rods. This was an engine designed with thermodynamic self-regulation. At its core, a system where the very increase in heat acted as a limit on the reaction rate. While TRIGA was a success of civilian engineering, Dyson's most ambitious work on engine efficiency occurred during his tenure on Project Orion. This was a project that married the science fiction of his youth, inspired by Olaf Stapledon and Jules Verne, with the brutal reality of nuclear physics. The goal was to build a spacecraft powered by the detonation of small nuclear bombs behind a massive pusher plate. Dyson realized that traditional chemical rockets were fundamentally limited by the exhaust temperature problem. In a chemical engine, the burning fuel must be contained within a combustion chamber. If the gas becomes too hot, the chamber melts. This imposes a strict limit on the specific impulse of the rocket. Orion bypassed this limit by moving the combustion outside the ship. The pusher plate would absorb the momentum of the explosion, while the heat would be dissipated into the vacuum. In a series of technical papers, Dyson outlined the absolute limits of this engine design. He categorized the Orion ships into two regimes based on their primary thermodynamic constraint: the energy-limited design and the momentum-limited design. In the energy-limited model, the primary constraint is the ability of the pusher plate to absorb thermal energy without melting. Dyson calculated that if a ship were to use a hemispherical copper pusher plate to absorb all the thermal radiation, the plate would need to be 20 kilometers in diameter and weigh 5 million tons. The efficiency of this engine was limited by radiative cooling. The ship would have to wait roughly 100 seconds between explosions to allow the plate to shed its heat. This design, while robust, was mathematically inefficient for interstellar travel, as it would take over 1,000 years to reach Alpha Centauri. Dyson's breakthrough came in the momentum-limited design, which utilized ablation. By spraying a thin layer of oil or graphite onto the pusher plate before each explosion, the excess heat would be used to vaporize the oil, which would then expand and provide additional thrust while carrying the heat away from the metal. This shifted the bottleneck from thermodynamics heat capacity to engineering momentum transfer. The limit was now the yield strength of the shock absorbers that connected the pusher plate to the crew module. Dyson calculated that available materials could handle a velocity transfer of 30 meters per second per explosion. This allowed for a ship only 100 meters in diameter to reach velocities of 10,000 kilometers per second, roughly 3.3% of the speed of light. Dyson's work on Orion was a masterclass in operational thermodynamics. He proved that by correctly managing the waste of a nuclear explosion, its heat, and prioritizing the transfer of its order, its momentum, humanity could theoretically colonize the solar system and beyond for a politically acceptable cost. The project was ultimately cancelled not by the laws of physics, but by the Nuclear Test Ban Treaty of 1963, a political limit that Dyson deeply regretted. In 1954, Dyson published an influential article in Scientific American entitled, "What is Heat?" In this piece, he aimed to demystify the core concepts of thermodynamics for a general audience of professional peers. He began with a provocative and simple definition. Heat is disordered energy. Dyson explained that energy can exist in two states, ordered and disordered. A flying bullet or a spinning flywheel possesses ordered energy. All its constituent atoms are moving in the same direction at the same time. However, when that bullet strikes a plate, the ordered kinetic energy is converted into random, chaotic vibrations of the atoms in the bullet and the plate. This conversion of order into disorder is the very definition of heat production. At high temperatures, it takes a vast amount of energy to create more disorder because the system is already highly chaotic. At low temperatures, a tiny amount of energy can create a significant increase in disorder. This realization was central to his later work on the far future of the universe. If temperature is the price of disorder, then as the universe cools, the cost of maintaining order, and thus the cost of thought, approaches zero. Dyson's most culturally resonant application of engine efficiency was his 1960 proposal for the search for artificial stellar sources of infrared radiation, now known as the Dyson sphere. He started with a basic question: if an advanced civilization's energy needs grow at a rate of 1% per year, how long before they outstrip the energy budget of their planet? The answer was roughly 3,000 years, at which point they would need to capture the total energy output of their star. Dyson argued that such a civilization would disassemble a planet, like Jupiter, to create a swarm of habitats and collectors that would eventually enclose the star. From a thermodynamic perspective, this shell is a heat engine. The star is the hot reservoir, and the shell is the engine that converts that stellar photon flux into useful work. According to the Second Law of Thermodynamics, this engine cannot be 100% efficient. It must reject waste heat. Dyson calculated that if the shell were located at a distance from the star where the temperature was comfortable for life, the habitable zone, the waste heat would be radiated away in the infrared spectrum, specifically around 10 micrometers. This provided a new operational strategy for SETI. Don't look for intentional radio messages. Look for the unintentional thermodynamic footprint of an efficient civilization, a star that has been blacked out in the visible spectrum but is glowing brightly in the infrared. In his Gifford lectures, later published as Infinite in All Directions and Origins of Life, Dyson applied his thermodynamic lens to biology. He famously disagreed with the replication-first school of thought, which argued that life began with a self-copying molecule like RNA. Instead, Dyson proposed a dual origin theory, where metabolism and replication evolved independently. Dyson viewed the first living things as metabolic droplets, coservates of proteins and enzymes that could consume energy and maintain a state far from equilibrium but had no genes. He defined these early cells as reproducing rather than replicating. Reproduction, in Dyson's operational terms, is a statistical process. A cell grows and eventually splits into two, with each daughter cell receiving roughly half of the metabolic machinery. Replication, by contrast, is a digital process. A precise copy of a blueprint is made. The thermodynamic advantage of metabolism first is robustness. A metabolic engine can survive minor errors in its protein hardware. A replicator, however, is subject to the error catastrophe. If the mutation rate is too high, the information in the genome is lost within a few generations. Dyson used the mathematics of phase transitions to show that a system of molecules could spontaneously jump from a disordered state to an ordered metabolic state once it reached a certain threshold of chemical complexity. Life, in this view, is a high-efficiency metabolic engine that eventually captured a genetic software system to improve its long-term stability. Dyson pointed to a striking biological fact to support this theory. The molecules adenosine triphosphate, ATP, and adenosine monophosphate, AMP, are chemically almost identical but perform vastly different functions. ATP is the fuel of the metabolic engine, transporting energy throughout the cell. AMP is a component of the RNA software. Dyson proposed that life's dual origin is reflected in this chemical similarity that the metabolic engine, ATP, was already in place when the replication software, RNA, AMP, evolved as a secondary, perhaps initially parasitic addition. The pinnacle of Dyson's work on operational thermodynamics was his 1979 paper, Time Without End: Physics and Biology in an Open Universe. At the time, the prevailing scientific view of the open universe, one that expands forever, was one of frozen despair. a slow descent into a state of permanent quiescence, where all energy is dissipated and life becomes impossible. Dyson challenged this thermal death scenario. He argued that as the universe expands and cools, life could survive indefinitely by adapting its metabolism to the decreasing ambient temperature. He based this on a postulated scaling law. The rate of energy dissipation required to maintain a certain rate of subjective experience is proportional to the temperature. Dyson's strategy for eternal intelligence involves cycles of activity and hibernation. Imagine a civilization with a finite store of energy. They do not expend this energy at a constant rate. Instead, they live in cycles. In each cycle, they expand a fixed fraction of their remaining energy. Dyson proved that the total number of thoughts, the sum of all subjective time, could be infinite even though the total energy consumed is finite. This is essentially a Zeno's paradox applied to thermodynamics. By thinking more slowly, as the universe gets colder, the civilization never runs out of energy. In the late 1990s, the time without end scenario faced a profound challenge. Observations of distant supernovae revealed that the expansion of the universe is not slowing down, as Dyson had assumed, but is accelerating due to dark energy, or a cosmological constant. Lawrence Krauss and Glenn Starkman published a rebuttal titled Life, the Universe, and Nothing, in which they argued that an accelerating universe imposes a hard limit on Dyson's eternal intelligence. A cosmological event horizon forms. Objects beyond a certain distance are moving away from us faster than light, and we can never access their energy or information. Furthermore, an accelerating universe has a temperature floor. Because of the de Sitter horizon, an observer sees a thermal bath of radiation known as the Gibbons-Hawking temperature. This non-zero temperature means that the cost of a bit of information will never drop to zero. If the temperature floor is, say, $10, negative $30 Kelvin, a civilization will eventually run out of energy and the engine of thought will stall. Dyson, ever the iconoclast, did not fully concede. He engaged in a decades-long debate with Krauss and Starkman, exploring whether intelligence could bypass this limit through reversible computing, a theoretical method of computation that does not dissipate energy. While Landauer's limit states that erasing a bit costs energy, processing a bit reversibly could, in principle, cost nothing. If a civilization could transition to a fully reversible computational architecture, the non-zero temperature of an accelerating universe might not be the death sentence Krauss predicted. Across his diverse career, Freeman Dyson's work was characterized by a specific intellectual move. He would take a grand philosophical question, where did we come from? Or, where are we going? And strip it down to a series of engineering problems governed by the Second Law of Thermodynamics. His definition of heat as disordered energy provided the foundational logic for this approach. If heat is disorder, then engine efficiency is simply the measure of how much order we can maintain as we transform energy from one state to another. In the RAF, this was the order required to get a pilot through a hatch. In Project Orion, it was the order required to get a pusher plate to absorb a nuclear blast without vaporizing. In the Dyson sphere, it was the order required to capture every photon from a star. And in Time Without End, it was the order required to maintain a thought as the stars themselves went out. Dyson's legacy is not found in a single theory of everything. Instead, it is found in the elegant mathematics he applied to the messy reality of the operational universe. He showed his peers that the limits of nature are not just constraints, but invitations to innovate. By understanding the thermodynamic bottlenecks of reality, humanity could, in his words, disturb the universe and shape its own destiny among the stars. He remains the preeminent frog. Of physics, a scientist who stayed in the mud of technical details and statistical facts, yet whose vision reached the furthest horizons of time and space. Freeman Dyson's work serves as a reminder that we live in a universe of hard limits, but also a universe where intelligence, by understanding those limits, can find a way to endure. As the universe continues its long expansion into the night, Dyson's operational thermodynamics remains the most sophisticated map we possess of the territory ahead. Thanks for watching. See you in the next video.